Bonjour. Alors aujourd'hui, nous accueillons Coralie Neiner. Coralie a soutenu sa thèse en 2002. C'était une thèse en co-tutelle avec la France et le Pays-Bas, et donc elle est aussi diplômée de l'Université d'Amsterdam. Après sa thèse en 2002, donc elle a effectué un postdoc à l'ESTEC, à nouveau aux Pays-Bas, et puis à l'Université de Leuven en Belgique. Et enfin, elle a été recrutée en 2006 au CNRS, d'abord au GEPI et actuellement elle est au LESIA. Dans ce que tu m'as donné comme information sur ton parcours, tu as oublié de mentionner que tu as été, il me semble, récipiendaire du prix jeune chercheur de la SF2A. Voilà, donc quand même un prix fort prestigieux qui montrait que tu avais un brillant avenir devant toi et qui se confirme avec un nombre de responsabilités de prise en charge de très nombreux projets. D'abord, Coralie est membre de l'Astronomy Working Group de l'ESA. Elle est, et c'est très important, co-PI de l'instrument Pollux sur le LUVOIR. Alors le LUVOIR, c'est l'extremely large télescope dans l'espace qui sera probablement le successeur du James Webb Space Telescope. Quelque chose peut-être pour 2030 ou quelque chose comme ça, 2040. Voilà. Mais bon, pour le long terme, mais d'avoir parmi nous une co-PI d'un instrument de ce très 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 grand télescope, je crois que c'est une chance. Elle est également membre de l'executive science team de Bright, membre de consortium de tests, plateau, PI de Life, BritePol, et de la base de données BES, enfin voilà, énormément d'activités scientifiques qui tournent autour souvent des étoiles chaudes, des champs magnétiques et de la sismologie, en particulier les étoiles BE, je crois que tu t'intéresses de très près. Et aujourd'hui, tu vas nous parler de l'origine et de l'impact des champs magnétiques dans les étoiles massives.
Tout à fait. Et j'avais prévu de parler en anglais, mais si vous préférez, je parle en français.
Le micro marche bien? Ça ne marche pas. Non? Ça ne marche pas.
Est-ce que c'est mieux?
Oui, c'est mieux.
Okay. So for those of you who are not familiar with stellar physics, I will first introduce what are the observations of these magnetic fields in massive stars, and then I will explain what is the origin of these fields. And then I will come to the impact that these magnetic fields have, first on the circumstellar environment, but also inside the star and on the evolution of the star. So first, which kind of magnetic fields do we observe in massive stars? There are basically three categories. There are the BP stars. These are hot stars that have strong fields and show chemical peculiarities, and this is why there is a P in their spectral type, P for peculiarities. And these are well known for many decades, so I will not talk too much about those. I will concentrate on what we call the magnetic massive stars. These are stars with magnetic fields of the order of a few kilogauss, and they were discovered only less than 20 years ago. And more recently, we found a new family of stars that have very, very weak fields below a few Gauss. They were detected only in a few stars, so I will only say a few words about those because we don't know much about them yet. So to study these stars, what we do is spectropolarimetry, and especially over the last 10 years, there have been several big surveys in spectropolarimetry. The first and biggest one was called MiMeS, and we observed more than 500 massive stars. Many, many measurements on the three high-resolution spectropolarimeters that are available in the world, which are Espadon at CFHT, Narval at TBL in the Pyrenees, and ARPSPOL at ISO in LESIA. After that, other surveys were also performed. They were concentrating on very specific kind of massive stars. The Bob survey complemented MIMES, but looking more at the southern stars at ISO. BritePol concentrated on all the very bright stars below magnitude 4. This was a complementary program to the bright constellation of nanosatellites. We had BinaMIcS that concentrated on hot binary stars. And more recently, we started the LIFE project, which concentrated on evolved hot stars. Okay? So with all these big surveys, we were able to say something about the properties of magnetic field in massive stars. We want to provide observational constraints so that we can test different theories and also develop new models. So in 2000, we discovered the very first magnetic massive star. And in the following years, we found about 30 of them. But it's only with the advent of these surveys that I just presented that we were able to get to a number that is significant and where we can do statistics. What we found is that the magnetic massive stars are very diverse. Some of them rotate very fast or very slowly. Some of them have strong fields, 10 kilogauss. Some have weak field, maybe 300 gauss. Some have peculiarities in their spectra, but others don't. So we really find all kinds of stars. And we do not seem to find something typical of a magnetic massive star. How do we detect magnetic field? We use the measure of polarization of the light, in this case circular polarization, Stokes V. What you will often see these kind of plots that show the average intensity profile of the lines in the spectrum, here at the bottom. At the top, we see a magnetic signature in circular polarization. So if the star is not magnetic, this curve will be flat. If it is not flat, if there is a signal, then that means there is a magnetic field. And often people will also show the null polarization, which is a test to see that nothing went wrong during the measurement. For example, some instrumental polarization that could have occurred, or some other physical phenomenon that would have disturbed the magnetic measurement. So you always want to find a signature if you're looking for a magnetic field, but nothing in the null polarization. This one should be flat to confirm that this comes from the magnetic field. So as the star rotates, this signature of the Stokes profile, either in circular or linear QU, will change. Just because you will see this magnetic field under various inclinations as the star rotates, this signature corresponds to the visible hemisphere of the field. So you can follow this change of the signature to derive the configuration of the field at the surface of the star. And so this is what we do. We take measurements of the Stokes profiles at various phases indicated here at the top. And as the star rotates, we see how this signature changes. And from this, we can recover the exact configuration of the field. For example, the inclination angle of the star or the angle between the magnetic axis and the rotation axis. And of course, the field strength. So what we find is that in most cases, the field is very simple. It's just a dipole that is inclined compared to the rotation axis. So what you see here on the left. There are very few cases where the field is more complex, and the most well-known case is this one, HD 37776, where the field is much more complex than a dipole, but this is the most extreme case, and they are very rare. The field at the surface of massive stars, whether they are simple or complex, are weak, so a few kilogauss. I say weak compared to, for example, white dwarfs or so. And they are stable. Even the stars that we discovered 20 years ago, we continue to observe them, and we do not see any change in this magnetic field. The only change we see is the rotational modulation because of the inclination of the magnetic axis to the rotation axis. So that's just rotational modulation, but the field configuration of strength does not change with time. So if we do some statistics, for example, with the MiMeS sample, we find that about 10% of all the massive stars we observe have a magnetic field. This is the same for O stars, B star, or A stars. There are only two exceptions, the OF P stars. Yes, this is a spectral type that actually exists. And all of the OF P stars have a magnetic field. And this is simply because this peculiar signature that we see in the spectra, that's called F P, it is due to the presence of a magnetic field. So from now on, we know that if you see this signature in the star spectrum, you know that there is a magnetic field even if you've not measured it. The other exception is the classical BE stars. These are stars that eject material to form a circumstellar disk around them. And for this star, we detect much less magnetic fields. In fact, we have no direct detection in any classical BE star, but we have some indirect indication for at least one of them. And when you look at the distribution of the field strength, which is plotted here, you see that it peaks roughly at 3 kilogauss. This is in log scale. So 3.5 here is about 3 kilogauss. And it's the same whether you look at hot B stars, AP-BP stars, or O stars here in red. You have the same distribution. It peaks at 3 kilogauss. Then you have less and less star when you go to stronger field, and also less and less star when you go to weaker field. But we find no correlation between the field properties and the star properties. Whether the field is strong, weak, inclined a lot or not a lot, whether the star rotates or not, whether the mass is higher or lower, there is no correlation between these parameters. So that is very different from what we see in cool stars. Here in hot stars, we have these simple fields that are stable, that are not correlated with the stellar properties, while in cool stars, like the sun, we see dynamo fields. So they are very active. They change all the time. They are generated by the star, and they are on small scale at the surface. So these are two families of very different fields, the hot star fields and the cool star fields. So what is the origin of this field in hot stars? Since the star has no convective envelope to create that dynamo that we see in solar-type stars, instead we could imagine that it has a dynamo in the convective core. Because in hot star we have a convective core and a radiative envelope. So we could create a dynamo in the convective core. That works. However, the time that you need to transport this magnetic field from the core to the surface of the star is longer than the lifetime of the star. So you will never see this field from the core emerge at the surface. So this is not the fields that we do observe. Maybe they exist, but we do not see them at the surface. So another possibility is to try to make a dynamo in a radiative envelope. A lot of theoreticians have worked on this over the last 15 years. They tried many kinds of dynamos. None of them worked. The most famous was the first one proposed by Spreit, now called the Spreit dynamo. So when you want to do a dynamo, you need to transform an axisymmetrical poloidal field into an axisymmetrical toroidal field. This is easy. As soon as there is differential rotation, you can use the omega effect. No problem to do that. But then you need to transform this axisymmetric toroidal field into a non-axisymmetric instability generated field. And there we can agree that it is possible in hot star from the Taylor instability. The Taylor instability just says that if the field is purely toroidal, and in fact later it was shown that it also works with purely poloidal, the field will be unstable. At some point the pressure perpendicular to the axis of the field will create an instability and destroy the field. So that also works. But the problem is how to close the loop. If you want to do a dynamo, you need to regenerate either the axisymmetric poloidal field or the axisymmetric toroidal field to make a loop, a small loop or a big loop. And that's how we get a dynamo. If you don't close the loop, the field stops. So Spreit proposed to do a small loop here using the shear to regenerate this axisymmetrical toroidal field. But Jean-Paul Zahn and collaborators later showed that this does not work. Shear alone does not work to regenerate this field. So Jonathan Braithwaite proposed an alternative with a big loop here, using the omega effect, again, differential rotation. That works for a while, but this produces a decrease of differential rotation with time, and so little by little the dynamo will stop. So it also does not work. Finally, the only one that works theoretically is the one proposed by Jean-Paul Zahn, which is to use the electromotive force of the instability to regenerate the poloidal field. That works on paper, in theory. But when they've put this dynamo in simulation, they were not able to excite it, or if they forced the excitation, it was not sustained and it would die. So even this that seems to work on paper does not work in the simulations. Moreover, from an observational point of view, if there was such a dynamo, we would expect correlation between rotation and the magnetic field, because here we use the omega effect. So there is a direct link between rotation and the field, and we do not see that in the observations. So we had to discard this possibility as well. Now I said that the stars, massive stars, have a convective core and a radiative envelope, which is generally true, but they also have a very, very thin convective layer just below the surface. So people have proposed that maybe it is in this very thin subsurface convective zone that the field develops. That could work also, but here you see an example of the strength of the field in colors versus temperature and luminosity. So you see for B stars or for O star, the strength that these fields would have at the surface. And looking at this scale above here, you see that it's of the order of a few tenths of Gauss. So that does not match the few kilogauss that we see in the observations. Moreover, if you make this kind of dynamos just below the surface, you will create small-scale fields, and we see big dipoles, so that also doesn't match. So whether these fields exist or not, we do not know, but at least they are not the ones that we observe. Okay, so we needed to find yet something else, and it was proposed that these fields are fossile. What are fossile fields? These are fields that come from the magnetic field that was present in the molecular cloud when the star was formed. So the molecular cloud had a magnetic field. When it collapsed to create the star, some of this field was trapped in the star. So this acts as a very weak seed field. And then at the beginning of its life, the star is fully convective. And so a dynamo can develop everywhere in the star and enhance this original weak seed field. As the star evolves towards the main sequence, there is a radiative core that develops, and theoreticians have shown that when this core develops, the convective, the dynamo field, will relax onto a dipolar configuration like the one that we observe. Then the star becomes fully radiative, and then the dipole is stable and doesn't change anymore. This stable dipole can be either aligned with rotation or it can be inclined compared to rotation. But in any case, even if it was aligned at this stage, when the convective core starts to develop inside the star, the interaction between the core and the radiative envelope will create an additional tilt of the dipole. So in the end, you have an inclined dipole in any case, even when it was aligned at this stage. So that works analytically. Oh yes, this was just to show you that we did simulations of the interaction of this convective core with the fossil field in the envelope. And indeed, it was shown that it changes the orientation of the fossil field, but it also strengthens the dynamo field in the core and has other impacts. Okay, so this dynamo field, this fossil field, they were studied analytically. It was shown that they exist. They are stable. They are oblique dipoles. And they are a mix of toroidal and poloidal components. They were also put in simulation, and in simulation it was shown that they remain there, they are stable, and it works all very fine. So it was concluded that this fossil field corresponds to the one that we see. So the origin of the magnetic field in massive star is fossil. It comes from the field that was there before the star was formed. A study of PMS massive star, so her big star, showed that this field already exists in her big star, also with the occurrence of 10%. And so we confirm also that already in the early stage of the star we see them. Finally, in the BinaMIcS study, which I presented earlier, where we studied hot binary systems, we searched for magnetic fields as well, and we found very few. There are much less magnetic massive stars in binaries than in single stars, about 2% instead of 10%. And this is also compatible with the fossil field theory, because people who study stellar formation have shown that if the medium has a strong field, it is much more difficult to fragment the cores to make several stars. So it's more difficult to make binaries when the medium, the original medium, was strongly magnetic. So if there is no field or very weak field, you will make binaries, but they will not be magnetic. And if you have a strong field in the medium, you will make single stars, and some of which will be magnetic, but then they are single stars. So this also matches the fossil field theory. Now, why 10%? I say 10% of the stars are magnetic. Why 10? Why not 50? Why not all of them? It is because of the initial conditions. So it was shown that if you change the initial conditions in which the star is formed, and in particular the magnetic helicity that is in this interstellar medium, you will change the proportion of stars that can reach a stable equilibrium of the magnetic field. So we know from observation that there is 10%, and then we can tune the initial conditions to have this 10% in the end. So in fact, we don't know the initial condition, but we can deduce the initial condition from the fact that we observe only 10% magnetic stars. What happens to all the others, the 90% that do not show this strong magnetic field I'm presenting? Well, if the field is weak, too weak, then the stability will not be reached. It will not relax on this stable configuration, and instead you can have an unstable, very weak field. This was proposed by Aurier et al. Another possibility is that the field is going to relax onto this stable configuration, but this takes time, and maybe you're observing the star when it has not yet reached this stable equilibrium. That's also possible. So the time it needs to reach the equilibrium is sometimes longer than the current lifetime of the star. So this theory says that 10% of the star are observed to be magnetic with this strong field of a few kilogauss. And then 90% of the others will have these unstable, very weak fields below 1 Gauss. These are maybe the ultra-weak fields I mentioned at the beginning of my talk. Some people talk about the magnetic desert in the middle, because for a long time we knew no stars with a field strength between 300 and 1 Gauss. In fact, we know now that it's not really a desert. There are a few stars there, but as I showed, there is a distribution of field strengths that peaks at 3 kilogauss, and so it decreases towards lower field strengths before this new family of ultra-weak stars starts. So there is a void there, but it's not completely void. So these ultra-weak fields, they have indeed been detected. If you look deep enough when you do spectropolarimetry, you add data collected over many, many nights for one single very bright, slowly rotating star. So you take the easiest case and you spend the whole week observing it all night. Then you're able to go down to magnetic field precision of the order of 0.1 Gauss, and you can actually detect them. So the first one to be detected with such a field was Vega, almost 10 years ago now. And after that, all the studies that try to do this manage to detect the field, as long as you observe deep enough. So for example, there was a study of 4 AM stars, and all 4 were found with a magnetic field. But you need to look deep enough. And this is more difficult if the star is more massive, because the radius is larger. So if the field inside the star is the same, at the surface it will be weaker than for a smaller star. So it is easier to detect these fields on A stars. It is more difficult on B. It is almost impossible on O stars. Still, they probably exist. So in the future, when we have even better instrumentation, we should be able to routinely detect this kind of ultra-weak field. But today, it's very difficult. We're only doing it on the easiest targets. Now, in passing, I also mentioned that some of these ultra-weak fields have signatures that look a bit weird compared to the usual stocks signature we normally see from the Zeeman effect. They have a big bump here centered on the line rather than a positive and a negative lobe. And this is explained by the slope of the magnetic field just below the surface. So when you have a fossil field and the star rotates fast, what happens? First, it has been shown that it does not impact the configuration. Even if the star rotates very fast, the stable configuration will be a dipole inclined compared to the rotation axis. But it is more difficult to reach stability when the star rotates fast. And this is the first explanation of why classical BE stars usually do not have detected magnetic field. Classical BE stars are very, very rapid rotators, above 90% critical. That's how they can eject their matter to form the disk. And so these very rapidly rotating BE stars have more difficulty to reach a stable magnetic field. But that it does not explain everything, because in fact we do know 2 rapidly rotating magnetic BE stars. These 2, they exist. So it is possible to have rapidly rotating magnetic stars. When the stability is not reached, as we just saw, you can still have an ultra-weak unstable field. So I am not saying that classical BE stars are not magnetic. They may be magnetic, but if they are, they have ultra-weak fields. They cannot have strong fields. Now, the real explanation why magnetic BE stars are not observed, it is because of the presence of the disk. From this simulation, it was shown that depending on the strength of the field impacts the disk, and it can disrupt it. So when the field is weak, 1 Gauss, for example, here you see 3 different strengths of field, and from left to right, time is passing. So you have a magnetic dipole of 1 Gauss and a Keplerian disk, and time passes, nothing happens. But when you put 10 Gauss, you start to interact with the disk, and if you put 100 Gauss, in fact, you disrupt the disk. And the conclusion of this simulation, it is that it is not compatible to have at the same time a BE disk and a strong field. If there is a strong field, it will disrupt the disk. It will then be one of these very rapidly rotating magnetic B stars I mentioned, but they will not be BE stars. So we're already seeing that the magnetic field can have an impact on the circumstellar environment. This is not the only impact that it can have around the star. It can produce magnetosphere. What happens is that the wind particles that escape the stars are forced to follow the magnetic field lines. So some particles escape from the positive pole, some particles escape from the negative pole, and they follow the closed loop of magnetic field, and they will collide at the magnetic equator. Because of that, material starts to accumulate there in the magnetic equator, and we get these magnetospheres. Because the magnetic field is inclined compared to the rotation axis, this magnetic equator is not the same as the rotation equator, right? So as the star rotates, we will see this change with time, with rotation. So we will see rotational modulation of many parameters. Of the spectral lines that are sensitive to the wind, that we observe in the UV resonance lines, of the emission that is emitted here by the disk itself, by the magnetosphere, so in H-alpha, in the infrared. X-ray emission also, because the particles that come from the two poles, when they arrive at the magnetic equator, they collide, so they make shocks, so this creates X-rays also in the magnetosphere. And of course, the light curve also, because this magnetosphere will eclipse the star with different angles. So an example here of the variation that we see in the UV wind lines. This is a doublet of carbon-4 observed at different times. And you see that the line shape and the equivalent width of this line changes with time, just because we are looking at the star under various angles. So we see either the magnetic pole and all the wind coming towards us, or when we see the equator, the wind is going in the other perpendicular direction, right? So we see more or less wind here, and we see this variation. If we measure the equivalent width of this line, and we plot it as a function of the rotation period, we can clearly see the rotational modulation. And so from this kind of data, we can deduce very precisely the rotation period of the star, even without measuring the magnetic field. But also the shape of this curve tells us something about the configuration of the field. What is the inclination of the magnetic axis compared to the rotation axis, for example? So we can deduce the magnetic configuration and the rotation of the star even without doing spectropolarimetry. And this is an example with UV wind lines, but this can be done with many other diagnostics. Like I said, you can look at the X-ray emission, you could look at the light curve to see the eclipses when the magnetosphere is seen edge on, polarization obviously, the magnetic field, H-alpha emission, etc. Many more that I'm not showing here. So whether there is a magnetosphere or not depends on some parameters. It's the competition between the strength of the field and the wind. So we've defined this magnetic confinement parameter, which is the field strength squared times the radius squared divided by the mass loss and the wind speed. And depending on whether this ratio is above 1 or below 1, the magnetosphere, well, the material will be confined in the magnetosphere. Now, still, you will have two kinds of magnetosphere. First of all, this material can only be confined up to the Alvan radius. That's where the magnetic field lines are closed. If you go further away from the star, the magnetic field lines are open. And then, of course, the wind particles, they just escape. But in the part below the Alvan radius, the magnetic field lines are closed, and the wind particles remain trapped along these lines. So that's the Alvan radius here. The particles that escape, they go at the magnetic equator in this magnetosphere, but they cannot stay there. They fall back onto the surface. So that's why we call this a dynamical magnetosphere. The particles are constantly renewed. The wind sends particles, they go in the magnetosphere, they fall back on the surface, and so on and so on. So there is always a magnetosphere, but it is constantly renewed. However, if the Keplerian co-rotation radius is smaller than the Alvan radius, so the Keplerian co-rotation radius is the position where gravity compensates the centrifugal force. So the position of this Keplerian radius depends on the rotation speed. If this Keplerian rotation radius is smaller than the Alvan radius, then in between these two radii, the centrifugal force will support the material that is there. And so the particles that arrive in this region, they are trapped. They cannot fall back onto the star anymore. And so we create what we call a centrifugal magnetosphere. Below that radius, up to the surface of the star, you still have a dynamical part on top of, in addition to the centrifugal magnetosphere. So these are two different types of magnetosphere, the ones that are more or less stable with material that accumulates there, and the ones that are completely dynamical, the material is constantly renewed. So these are two MHD simulations of this dynamical and centrifugal magnetosphere. You clearly see here what I was trying to explain, the material coming and falling back all the time. While here you have a more stable magnetosphere. In this simulation, we have also introduced what we call leakage. So sometimes closed loop can open and material can escape outside. But still you see a more stable magnetosphere here. These are 2D simulations, but now we do them in 3D. Just they are harder to understand. That's why I keep showing the 2D ones. Now, in the observation also, we can very easily distinguish dynamical and centrifugal magnetosphere just by looking, for example, at the H-alpha emission. When there is a dynamical magnetosphere, the material is close to the surface. And so you will see this kind of variation with an emission in the center of the line. This is the variation of the H-alpha emission as a function of time, rotation phase. So you see that there is emission, it is close to the center of the line. But in the case of the centrifugal magnetosphere, the emission will be in the wing of the line because it is further out. The centrifugal part is after the Keplerian radius and up to the Alvan radius. So these are these bumps here. These are the two sides of the centrifugal magnetosphere. So without knowing much about the star, without knowing the wind speed or the field strength, just looking at how the emission looks like, you can say if there is a centrifugal magnetosphere or a dynamical magnetosphere. This is now also done with infrared emission lines, and since very recently we have the Spirou spectropolarimeter that does spectropolarimetry in the infrared. Yesterday I received the first Spirou observation of massive stars, and we can very nicely see this kind of effects. So we created this diagram, which is the rotation versus magnetism confinement diagram. You just plot the Keplerian radius versus the Alvan radius. Or if you prepare, it is rotation versus magnetic confinement. So when magnetic confinement is below 1, there is no magnetosphere. But you see that all the stars are above 1. And you can separate this square in two triangles, the dynamical magnetosphere and the centrifugal magnetosphere, depending on whether RK is larger or smaller than RA. I have shown in red all the O stars. The O stars, you see, are almost all in the dynamical magnetosphere triangle. And this is because O stars have very strong winds. So their winds dominate, and they don't manage to make a centrifugal magnetosphere. There's one exception, which is the Plaskett star. It's a very special star with a very strong field and a companion. It's a very special case. But all the others are here. The B stars that are in gray often have a centrifugal magnetosphere, but not necessarily. That depends on the strength of their field. Now, this is the impact of the field around the star, but the field also has a very strong impact inside the star, because what we observe is the field at the surface, but of course the field is everywhere inside the star, and it is much stronger inside the star than at the surface. The first well-known impact is the impact on the chemical elements. That's what we see in the well-known AP-BP stars that we've observed for more than 60 years. There is radiative diffusion along the magnetic field lines, so the transport of chemical elements is different in the magnetic star. But also, if the field is strong enough, you can create chemical spots on the surface of the star. So here is an example. At the top, we see a magnetic dipole. And here we see two random chemical elements, lithium and oxygen, where you see the lithium is concentrated close to the magnetic pole, while on the opposite, the oxygen is concentrated at the magnetic equator. So it's just the presence of the magnetic field lines that force the element to go one way or the other. Magnetic field also has an impact if the star is pulsating. When there is a pulsation mode in a star, you can observe frequency peaks, okay? So the periods of the pulsation. How many peaks you observe depends on the order of the mode. Okay, so if it's a low order, you will observe, for example, if it's L equal 1 spherical harmonic, then you will have 3 peaks. If it's a higher order, you have more peaks. And this is called the rotational splitting. Because of rotation, the pulsation frequency is split. The same occurs with magnetic field. So you will get a splitting of the peaks because of the presence of the magnetic field. And the star rotates and has a magnetic field. The frequency are split twice, okay? So you will see many more peaks in a magnetic pulsating star than in a just non-magnetic pulsating star. That means that if you do not know that your star is magnetic, you will misinterpret the peak that you see, because you see, for example, 7 peaks. You will say, oh, wow, this is an L equal 3 mode. But in fact, it's just an L equal 1 that has been also split magnetically. Here I show 2 cases where just the obliquity, so the angle between the magnetic axis and the rotation axis, has been changed by only 10 degrees. And what you see between this series of peaks at the top and those at the bottom is that the amplitude of the peak is very different. So it's not just the presence of the field and its strength. The strength defines the size of the splitting, but also the configuration of the field, in particular the obliquity, that defines the amplitude of the peaks. And some of these peaks, for example, with beta is 105, will be detectable, while here they will be in the noise. So which peak you see and how many peaks you see depends on whether the star is magnetic, but also on the configuration of the magnetic field. And so it is very important if you do seismology, if you study pulsation, to know whether your target is magnetic or not. Otherwise, you will be completely wrong in your mode identification. The contrary is also true. If you're studying magnetic stars and you do not know that your star is pulsating, you will do something completely wrong. Here you see an example of beta sep, which is a radial pulsator, so the simplest case. You see how the intensity line changes with time because of the pulsation. And this deformation of the line profile also is impacting the shape of the Stokes V profile. So if you do not know that your star is pulsating and you're just studying the magnetic field, you're making a mistake in your model of the Stokes V and therefore in the configuration of the field that you deduce. So when the star is pulsating and magnetic, it is very important to consider both at the same time. So this has been done for a few targets. This is an example of a beta sep pulsator. And for this star, we did a seismic model. First, just looking at the pulsation. This star has a relatively high V sin I for a beta sep pulsator, so we expected in the model that there would be a lot of mixing inside the star because of the rotation. And in fact, we found that the best model is without mixing. And the reason for that is that the star is magnetic with a field of 400 Gauss, and the magnetic field inhibits the mixing inside the star. The same was found for a beta SPB pulsator, which was observed with Coro. So from the Coro Leica, we had a lot of pulsation modes that were detected. It rotates relatively fast, 50% critical, and it has a field of 1.3 kilogauss. And again, the best seismic model for this target has no mixing. This is understood in theory, and 2 authors have derived specific criteria to say above which field strength the mixing will be inhibited. So the Sprite criterion is here. I don't go into details, but basically it says that when the field has reached a certain strength, it will stop the differential rotation, and therefore it will also stop the mixing. If I take the case of the beta sep pulsator I just showed, the critical field above which there would be no mixing is for 40 Gauss. In the Zahn criterion, which is slightly different, he considered the magnetic Lorentz force to derive this criterion, but the result is the same. He says that above a certain field strength, it will remove differential rotation and the mixing. With this criterion, I get 70 Gauss. And the field of this star is 400 Gauss. So it's no surprise that indeed in this star, there was no mixing, because the field is too strong. So, of course, we would like to do this for many stars. If you can do that, if you have a pulsating star that's magnetic, you know in advance, using this criteria, that in most cases there will be no mixing. So if you can put your mixing parameter to 0 in your seismic model, you can much better constrain the rest of the model. So this has been done for only a few targets, unfortunately, because it's very difficult to find magnetic pulsating stars and to characterize in detail both their magnetic field and their pulsation before you can do a seismic model. So 3 stars were studied from the ground. Only 1 was observed with Coro, the one I just showed. Kepler, unfortunately, did not observe any magnetic pulsating hot star, simply because it was observing a very old field, a field where the stars were old because it was looking for exoplanets. So there were few massive stars, and none of them were magnetic and pulsating. But Kepler-2, which was a refurbished version of this mission, which observed in the ecliptic plane, observed many massive stars, and among them we found 6 that are magnetic and pulsating. And for now, only one has been characterized in detail. It is Iota Libri. Now, there is BRITE, a constellation of 5 nanosatellites that are flying and observing stars for seismology. And I mentioned that we've done the BritePol survey, which is a spectropolarimetric survey of all the bright targets. So any star that is brighter than magnitude 4. These are 600 stars, among which 300 are hot targets. And because they are very bright stars, we didn't find any new magnetic pulsating ones. There are some, but they were already known before, like those that I mentioned up there. Now, recently, we started to get the TESS data. TESS is a new mission for asteroseismology and search for exoplanets. And in there, we have identified many stars that show rotational modulation. So they are magnetic candidates. But at this point, we do not know if they are really magnetic stars. They are candidates because they show this rotational modulation. Now we need to do spectropolarimetric observation to check that they are really magnetic and then characterize their field. But some of them that show this rotational modulation are also pulsating. So we are confident that we will have nice targets from the TESS mission. And in the future, there will be Plato. That's only in 2026, but Plato will observe a large part of the sky, including very bright stars, and will provide very, very nice data, longer light curves than TESS. And so this will be perfect for this kind of magneto-asteroseismic studies. So this is the impact of the magnetic field inside the star that we can study with seismology. Now, the final impact I want to talk about is the impact on the evolution of the star. We don't know much about that yet. So we want to know, first of all, how this fossil field evolved with time. The fossil field that we have studied were on the main sequence. I said that they don't change, but is it true in later stages of evolution? Is there just, magnetic conservation, or maybe something modifies, interacts with the field and changes them as the star evolves? And what is the impact of the field on the evolution of the star itself? Because when there is a magnetic field in a star, you modify the transport of angular momentum, you modify the mass loss, you modify the internal rotation profile, you modify a lot of things. So the evolution of the star will change. It will not be on the same evolutionary track anymore, and the end of the life of the star will also be different. So it is very important to take into account this magnetic field on the evolution of the star. And even it could impact, for example, the supernova, because the magnetic field that is present before the supernova explosion contributes to the energy budget of this explosion. So the supernova will be different if there is a field or not. So the simplest idea is to say that the magnetic flux will be conserved as the star evolves. Okay, so we have a magnetic field and it stays there. But as the star evolves, its radius increases. And because the radius increases, the field that we can measure at the surface decreases. It decreases as the square of the radius, just to conserve the magnetic flux. You have a bigger star, you thus have less field at the surface. If we take a typical magnetic field strength of 3 kilogauss on the main sequence, and we follow the evolution along the evolutionary track, the field quickly decreases. After the main sequence, it's already only 300 Gauss. And this dashed line are ISO field strengths. So here you have 300 Gauss, here you have 100 Gauss, 10 Gauss, and here at the end on the right side of the plot, you only have 1 Gauss left at the surface. So first of all, it means that studying this field in evolved star will be very difficult because they are very weak. But also it decreases very fast, so we should see this effect really clearly in principle. In addition to magnetic field conservation, there could be some magnetic decay due to other physical process, simple ohmic decay, for example. And some people have shown hints that this may be occurring. The first one was John Lenstreet. This is the field strength as a function of the fractional age on the main sequence, so from younger to later younger to older stars on the main sequence, and he showed that the stronger fields are in the younger stars. So that was the first hint. Later, other people have tried to do this, check if there is a decay. Most of the points here with their error bars would be compatible with a flat line and no decay. But the recent study by Schultz et al. That is about to be published have added these 3 red points, and there you clearly see that it is going down. So there would be some decay here. However, this is a bit controversial because if you don't believe this last point, for example, there's not much of a trend anymore. So this is still very preliminary and highly debated. But okay, there could be a hint of magnetic decay. So let's look at magnetic hot evolved stars. We knew until last year only 2, Zeta Tauri A and Epsilon CMA. But when you look at the evolutionary stages of these 2 stars, first we are sure that they are magnetic, but this one is just past the main sequence, and this one is at the end of the main sequence, not even outside the main sequence yet. So they are a bit more evolved. They are the most evolved of all the ones we know, but they are not so evolved in the end. So they are not good targets. We need to find better ones. In the BritePol survey, we did find 2 that are clear supergiants. If you look at their evolutionary stage here, they are well past the main sequence. So these are clearly evolved. They are supergiant magnetic stars. And they are also very clearly magnetic. Here you see the signature. There's no doubt that they are magnetic. So these 2 stars are a good example of magnetic evolved stars. Their magnetic field at the surface is 3 Gauss and 6 Gauss. So you see, indeed, it is very low as we predicted. Unfortunately, when you put these stars in a Keepin diagram, that's a Keepin diagram, it shows the structure of the star. So this is the radius. Here at the bottom, you're in the core of the star, in the center of the star. And the red line shows the surface of the star. And from left to right, it's the time passing. So here the star had a convective core and a radiative envelope. And as it evolved, at the end here, it has also a convective envelope outside when it is a supergiant, right? So you're following the evolution of the structure of the star with time. When you look at this Keepin diagram for these 2 targets that we found with BritePol, you see that one of them, the position where they are in this evolution, is the vertical blue line. One of them is here just at the transition where the convective envelope will develop. So that's not very convenient for the kind of studies we want to do. And the other is past this transition. It is where the convective envelope has already developed, but it has a superseen convective envelope. So the impact of that will probably be negligible. So this is also not a good target. So we were unlucky that the 2 that we found, they were not good. So we decided we need to find better ones, and we created the LIFE survey. So it's a new spectropolarimetric large program to search for magnetic evolved hot stars. So we are targeting stars with luminosity class 1, 2, or 3. So after the main sequence, we're only looking at OBA stars, so hot stars, and we try to get measurements with a precision below 1 Gauss to detect these weak fields. We started over 2 years ago. We have observed 33 targets now, only 33 because each of these measurements takes a lot of time to reach this precision. We are doing the observation with Espadon and Narval. And we found many. So I give here 4 examples. Again, an example of the magnetic signature to show you that the detections are very clear. Here are examples of where they lie on the evolutionary track, so they are clearly evolved. For these 4 examples I'm mentioning here, which are typical, the strength is 3, 3, 9, and 6 Gauss at the surface. In fact, we found many more than those 4. We found 7 that have clear magnetic signature, plus 2 where the signature is not so clear. We consider them as candidates, and we are going to reobserve them. So we could have up to 9 magnetic detection. Now, if you look at these magnetic field strengths I mentioned, 3 Gauss, a few Gauss, and you look at the age of the star, and you calculate backwards what was the strength of the field on the main sequence, you get to a few kilogauss. So the fields that we indeed observe on the main sequence. So just assuming magnetic flux conservation, you get something coherent on the main sequence for the magnetic field strength. So the fields we observe are compatible with magnetic flux conservation. But that does not mean there is no decay. Okay, we will only know if there is a decay or not once we have enough statistics and we can reproduce the distribution of field strength and see if it peaks at 3 kilogauss as we observe on the main sequence. If we take all the fields that we observed in the evolved stage, bring them back with magnetic flux conservation to what they were on the main sequence, and the distribution peaks at 3 kilogauss, it means that there is just magnetic flux conservation. If it gives distribution that's different, higher or lower than 3 kilogauss, then there is either magnetic flux decay or enhancement. That we can only do once we have enough statistics, not with 7 targets. So we will continue the live project. Even with these small statistic numbers, there's one clear thing that comes out is that we have a lot of detections. With 33 stars observed and 10% magnetic star, we should have found 3. And we have between 7 and 9. That's already significant. We have more than, say, about 25% detection rate instead of 10%. What is the reason for that? Probably we start to see the dynamo field that develop in the convective region. If I go back to this example here, as the star evolves, a convective region develops here, convective zones or convective layers, depending on the case. And in this convective zone, you can have a dynamo. And this dynamo will also interact with the fossil field that is in the radiative layer below. So probably what we see is not just the evolved fossil field, but also new dynamo fields that have started to develop. And maybe we even see the interaction between the two, because as I showed in the beginning of my talk, when there is a dynamo in the core, for example, and a fossil field in the radiative envelope, we know that there are interactions that increase the dynamo field, that change the obliquity of the fossil field. The same kind of things could happen here. There will be interaction between this new dynamo field and the fossil field, and so that could also modify the fossil field, maybe increase its strength, and that's why we see more of them. Okay, so to conclude, I want to summarize what I said today. First of all, that the magnetic field of massive stars are very simple. Usually they are oblique dipole, dipole inclined compared to the rotation axis. And these fields are of fossil origin. They come from the seed field that was in the molecular cloud before the star was formed. 10% of all massive stars are magnetic, with the exception of OF P star, which are all magnetic, and classical BE stars, which are not strongly magnetic. And all the others, 90%, they could still have magnetic field, but ultra-weak ones, of the order of a Gauss or less. If the star has a magnetic field, it will have a magnetosphere, and there can be two kinds, the dynamical ones or the centrifugal ones, depending on the relative competition between the magnetic field strength, the wind speed, and the mass loss. If there is a magnetic field, it will also inhibit the mixing inside the star. It can produce chemical spots at the surface. It will interact with the pulsations. And so it isn't important, if you do seismology, to take the magnetic field into account and vice versa. So you have to do magnetoasteroseismology if you want to do things properly. Finally, as the star evolves, the magnetic field is still there. It is compatible with magnetic flux conservation at first order. And we find many more fields, as I just showed, than on the main sequence. And this is probably because we start to see the dynamo fields that develop in later stages of stellar evolution. And that was it. Thank you.
Thank you very much. Questions?
Just two short questions for a non-specialist. How do you distinguish between dynamo and fossil, in the observations fields? And my second question is that you said that in the binaries you see much less magnetic field. Now, is there any dependence on the environment, for instance, in the star cluster, globular clusters, or not in the field? Or?
So your first question, we see this in the shape of the Stokes profile. So when we see the signature, if it's a dipole, you will see a positive lobe and a negative lobe when the pole is facing you. And as the star rotates, this shape will change from positive negative to negative positive. and that's just a dipole. If you have a dynamo field, you have small scale structure, and then your signal will be with small structures. So it's very different. So it's easy to distinguish, unless the V sin I is very small. When the star rotates very slowly, and the line is very narrow, you may not be able to distinguish this very complex structure. So these are more difficult cases. Your second question was? The binaries, yes. Unfortunately, we do not have enough statistics to really say that, because we find so few magnetic binary stars. Some are in clusters, but not all of them, and so we don't have the statistic to really say if the environment impacts. We think it should, because of the stellar formation models that I showed. They said that depending on the strength of the fields in the environment, you will form binaries or not. So there should be a link, but we cannot see it observationally.
Even for the single stars, is there a relation?
No, for the single stars, the ones that are in cluster do not show anything different than the others.
Questions? I have one question regarding the fact that the binary star formation, what about the planetary system formation? Does the magnetic field have an impact on the planet formation?
In the cool stars, yes. In the hot star, we have no planets around O stars or early V stars.
No.
No. It would be very difficult to form one close to the star and to have it survive. But if you go to cooler stars, then you can have planets. And of course, the magnetic field has a huge impact. First there is the irradiation of the star, but because there is a field, there will be the magnetosphere. If the planet also has a magnetosphere and the star has a magnetosphere, they might interact. You can get this bow shock in between that you can see in the UV, for example. And so it's the interaction between the two fields. It's just like for us, you know, the sun and the earth have their magnetosphere interact, and that's why we get the auroras and everything. So it's the same. But for the very hot stars, the massive stars I'm talking about, we see no planets.
Okay. Because we don't know. Okay. I have a question regarding the criterion for inhibition of the mixing.
Mm-hmm.
There was two criterion, the Zahn and the Sprout one.
Yeah.
And I found
yes,
very surprising that the two equations you mentioned are so much different, and you find the same order of magnitude for the magnetic field. So it's wonderful.
They are not so different.
How can you find similar numbers with so different equations?
Well, if you look carefully at the physics in these two papers, it's not so different, okay? Jean-Paul has looked really at the Lorentz force, and starting from this, he has tried to see when the differential rotation would stop. And Hengstpreut did it in a different way, but in the end, these two equations are not that different if you really compare.
Really?
Oh, this is B square, and this is B. Okay, so you have the 4 pi rho, you have R square, sigma. And, but then there is this coefficient here that you should compare with the time. This is the time during which the star has lost angular momentum, this TAM. And that goes with this in the Spreut criterion. It is slightly different, but it's not so different.
So you're not surprised by the result?
No.
Okay. Yes?
Do you detect any precession of the magnetic field with respect to the rotation of the star, or they are just moved together?
So how, you mean whether the obliquity changes?
Yes.
No, the fields are stable. So the ones that we've observed for 20 years, the first one we discovered, they have not changed. There was one claim of a change in a star by Alessian et al. It was I forgot the name of the star, but there is one claim, and in fact it was a problem in the observations. So this was later refuted. So no, the configuration does not change with time.
What is known about the relation between the magnetic field of white dwarfs and the magnetic field of their progenitor star? Because low mass white dwarfs come from G star, F star, which have a convective envelope and have a
It's a very good question, and we've looked at it, but we've not found a correlation. So there's so many things that happen in the evolution of the star before it becomes a white dwarf that basically the distribution of field in white dwarfs cannot be linked to the distribution we see on the main sequence.
So thank you very much. You can applaud the speaker again.
Thank you.